In this lecture, we're going to talk about an application of the singular value decomposition to image processing. So remember that the singular value decomposition is a way that we can write any matrix, regardless of its size or dimensions, in the form U times sigma times V transpose, where sigma is a not quite diagonal matrix, and U and V are orthogonal matrices. But rather than looking at the full singular value decomposition, we can approximate a matrix by simply selecting the k largest singular values. Remember that typically when we look at the singular value decomposition, we write the singular values in decreasing order. So if we look at v1 through vk being the corresponding orthonormal columns of the matrix capital V, corresponding by the k largest singular values. And similarly, we can define ui in the form a times vi equals sigma I ui. Now, if you're not sure about this notation, I recommend you go back and watch the previous lecture where we defined the u's and the v's and the sigmas and all that stuff. So now, rather than using the full matrix sigma, we're going to use a truly diagonal matrix D, which is a diagonal matrix whose diagonal entries are the sigma 1 through sigma k. P is going to be a matrix whose columns are v1 through vk. It won't be square anymore, typically. And then Q is going to be the matrix whose columns are ui, uk. Now A, which equals the matrix U sigma V transpose, is going to be approximately equal to the matrix Q D P transpose. The more singular values we use, the closer that approximation will be. So what is this good for? Well, let's consider this image. We can think of each pixel of this image as an entry of a matrix. And since the image is in black and white, we can think of each entry of that matrix as being a number between 0 and 1. Where 0 might represent black and 1 represents white, or vice versa. Now this image happens to be 752 pixels by 1003 pixels. So if we wanted to represent this image accurately, we would need 752 times 1003, which turns out to be 754,256. We'd need that many numbers between 0 and 1, to store this image. Now that's a lot of numbers, so what we might be interested in doing is compressing the image to store it using less space in exchange for sacrificing the 100% accuracy of the image. So when we display the image, it might be grainy, it might not be 100% accurate to the way that it looks when it's perfectly recreated, but it might look good enough in exchange for taking up much less space to store. And the approximation using the singular value decomposition gives us a way to do this. We can choose how many singular values we want to use. If we use just a few singular values, then the image will take up much less space, but when we recreate the image using this approximation, it won't look exactly like what it looked like originally. If we use more singular values, we'll need more space to store the image, but it will look more like the original image when we recreate it. So as an example, let's use the letter capital M to represent the original matrix that represents the original image. Remember that was 752 by 1003. And let's say that we want to use 50 singular values. Then M will look like Q, D, P transpose, approximately. And D, remember, is a square matrix, and that's going to be the dimensions based on how many singular values we choose. So in this case, 50 by 50. Q is going to end up being 752 by 50, and P is going to be 1003 by 50. And if we add all that up, that means that we only need about 90,000 numbers to store this image, and that's an 88% reduction in size from the original 750-some thousand. So obviously, because we're using such large images, this definitely wouldn't be something we would want to do by hand. We want to use some technology. So here's how we might do this using Mathematica. So first we import the image. And in this case, the original image is actually in color, so I'm going to convert the image to grayscale for the purposes of this example. Now I'm going to use the image data command, which converts the image file to the matrix that we were talking about. So notice that each entry of this matrix, and obviously Mathematica isn't showing me all of the entries here, but each of these entries is a number between 0 and 1. And that represents the grayscale of how light or how dark each individual pixel is. And now we're going to use the singular value decomposition command. If you recall from the previous lecture, that outputs a list of 3 matrices, which I'm just going to call U, V, and W here. Now the approximation is going to be U times V times W transpose. And so this matrix is the same size as the original matrix, but it's only going to be an approximation of the original image. Let's take a look and see how well this compressed image represents the original image. So this is what we get when we convert the approximation matrix back into an image form. Notice that the primary features are still there, but obviously the image is very grainy and some of the details aren't quite there. And this is the trade-off that we get for having the image take up much less space in storage. So the less space it takes up, the less accurately it gets recreated when we put it back into an image form. Now, if we want to do this with a color image, we can do that, and often one way that we can do that is separate an image into its red, green, and blue components. In that case, we perform the singular value decomposition separately for each color component, and then we recombine the resulting image. Here's what it looks like when we do it on the original color image of this pier. So the image on the left is the original full-size image, and the image on the right is the recreated image, again using 50 singular values. We can definitely still see the primary features, and the colors are in the right places. The boat is white, the sky is blue, all the things that we would be looking for are there. But it again is noticeably grainy. We've got some little artifacts. We've got this, the bird is obviously smeared out. We can't really see that's a bird at all. So again, it's a trade-off between storing the image in a smaller amount of space versus having the image recreated 100% faithfully.